Hi guys. So first thing I want you to do today is go into Schoology and go to our week 2 and then grab this surface area classwork because I put a big old warm up in there today and I think it's probably good for all of us to practice setting these up. So you can just worry about setting them up and getting them in your calculator. But pause the video and take some time to work through these problems and I'll be sure to post answers as well. So let's pause the video and then work on our classwork. All right, you're back. So with these, let me know if you have questions. I was thinking I would just post the answers and then make sure that you guys are doing okay. It's always easier, I guess, on my end because from x equals 0 to x equals 2. So we're just looking at, see if this weird situation that kind of gets cut off because it doesn't get all the way there. And then, of course, when you revolve it around these horizontal lines, these would be disk washer methods. And when you revolve it around these types of vertical lines, that's when you should be expecting Shaw methods, okay? The washer, in this case, like y equals 7, is because I have this hole up here, whereas this is filled in. And then my radius should always be coming off of my axis of rotation. So remember to attach your radius, that's a totally radius, to your axis of rotation. Let me know if you have questions. I'll make sure these are posted. I'll post yesterday's as well. But here are these. Let's see, let me scroll down a little bit. And then I also did put that arc length one on here. So again, let me know if you have questions. So today we didn't have a whole lot new to talk about. We just need to talk about surface area. So we know surface area is the area around the outside of our curve. So of course this is calculus. So what we're doing is we're taking some function and we're revolving it around some line to make some solid. So revolve f of x to create a solid. And we want to find the surface area. There's all sorts of reasons why we might need the surface area of our odd solids. But maybe we're painting our alien spaceship today. So what I want to do is I want to continue to think about this like I always tell you guys in calculus terms, right? So if I were to take my little tiny thin slice of this, as I send it around, I imagine how it would make like a little tiny circle. And if I think about the perimeter of that circle, then that would give me the like basically like the area of that, right? Perimeter of the circle times a little tiny like width of my circle, right? Times like my width of my circle. So this little step that we take, we talked about yesterday, because that's like the width of this is like a little distance along my f of x. So what I'm hoping you guys are realizing is this width is a tiny piece of our arc length. Which is why we do surface area after arc length, because surface area is kind of arc length circle. So if I need my perimeter of my circle, we know that that's 2 pi r, right? R is going to be measured from my axis of rotation. Distance to f of x from our axis of rotation. So what that leaves us with is that our surface area, if I get it right, Of course, you know, we have our arbitrary like a to b that we want to do, is going to be the integral of 2 pi r times arc length. Okay. Now r is going to be our distance from f of x to our axis of rotation. This is essentially going to be the absolute value of f of x minus your axis of rotation, because we will always do this in some sort of like top minus bottom. Of course, this is assuming that we have a horizontal axis of rotation. But we generally do this in some sort of top minus bottom. So I guess it depends if our f of x, right, is above or below our axis of rotation. Okay, and so that's where that issue is there. So let's clean this up a little bit. Arc length we talked about yesterday. Arc length is has a formula, right? So our surface area, whoops, would help what I was writing. Our surface area is 2 pi, the integral from a to b, and I'm going to call that still r of x, which is my distance from my axis of rotation to my f of x. Arc length is 1 plus the derivative of prime of x squared dx. And r of x equals that. Oh, I guess I wrote it like 15 times, but it's our distance. F of x, axis. I promise that it's really not too much of a leap. I guess the biggest leap is like where the formula comes from for me. And then once you guys have the formula, then I think that you feel good with it and you know what to do with it. So for me, it's sort of this idea of I took my arc length and I kind of rotated my arc length like 2 pi r, and then I found all those little tiny basically perimeters and added them. Okay, let's go ahead and look at an example, and then you guys can let me know if you have questions. So we're going to find the surface area of the surface created by revolving x cubed around the x-axis from 0. So thinking about our graph, x cubed is this little buddy, y equals x cubed, 0 to 1, it's relatively boring. Here's x equals 1, intersects at 1, 1. Of course, our intersection point over here is at 0, 0. Where's my little highlighter pen? Because I have that stupid thing open. It's in my room. So here's the area we're revolving. And then I like to think about where I'm revolving it around. So it's around the x-axis. So going here. Oh, and I didn't mean to fill that in. I've been doing way too much volume. Because we want surface area. Helps to read. So we remember surface area is the integral from a to b of basically our circumference, so that 2 pi r times our arc length. Okay, and r is the distance from our axis of rotation to our function we're finding the arc length for. So here's our function we're finding our arc length for, right? Surface area, I'm sorry. And here is our axis of rotation. So this distance in between would be my r. And r is changing, right? R starts out little back here, and r ends up bigger when we're here at our limits. So as we go along, we realize r is this top minus bottom, so r is my f of x minus my axis of rotation, which is really just x cubed minus 0, which is avoiding x cubed, okay? Arc length, we remember, whoops, yellow's not going to work very well. Arc length, we remember as the integral from a to b of the square root of 1 plus our derivative squared dx. So our derivative, well, our f of x was x cubed. So our derivative is 3x squared. So we need to integrate from, and I feel good with you guys on this part, x equals 0 to x equals 1. I don't think that's a big difficulty of ours. The 2 pi is here because of the surface area formula. R was x cubed, because it was just x cubed minus 0. The square root of 1 plus 3x squared squared dx. Okay. Now this one, of course, is a lovely book problem, so it works out nicely. But in general, calculators are our friend. We will need our calculator to do most integrals for surface area. And it's just because of that square root. Now, one thing that's nice about surface area is because we have this r of x, what happens often, at least with book problems, is we have an opportunity to potentially like maybe u sub this guy because we have a function out here. So that's always something to look for if we don't have our calculator or if we need to be showing our work. So let's go ahead and simplify this, and we realize this is 1 plus 9x to the 4th squared, right? And then when I'm looking at this, what I see, and this is probably math teacher coming in, but what I see is the degree inside is x to the 4th plus a constant, not a problem from a derivative, and this degree is 1 less. 1 less specifically is great for derivatives because it lends itself well to a u sub, right? Because every time we take a derivative, the power goes down by 1. So if we try to make du be the stuff inside, then du, stuff inside the square root, because that square root's going to be problematic for sure, would be 36x cubed dx. And that's wonderful because we have an x cubed there. So we go 1 over 36 du, and we get x cubed dx, which we have here, x cubed dx. And that gives us, oh gosh, and we can't forget to fix our limits of integration, although it's not too bad here. When x equals 0, u is 1 plus 9 times 0 to the 4th, will be 1. When x equals 1, u is 1 plus 9 times 1 to the 4th, which is 1 times 9 plus 1 is 10. So we have 2 pi integral from now 1 to 10 of du over 36 times the square root of u, right? Oh, that was a really terribly gross order that I wrote them in. So let me change that to the square root of u du. And then we realize, oh, this is actually something that we can definitely integrate. I'm going to reduce that to pi over 18 from 1 to 10 of u to the 1/2 du. Remember, if we write our exponent or our roots as exponents, it makes our life much easier. So pi over 18, integral of that is u to the 3/2, 2/3 of that, 1 to 10, which leaves us with pi over 18 times 2/3 times the 10 to the 3/2 minus 2/3 times 1 to the 3/2. I'm going to pull the 2/3 out so that it becomes 2 pi over 3 times 18. Just bear with me. 10 root 10 minus 1. And then this will reduce to 9. So this is pi over 27 and root 10 minus 1. Beautiful. Okay. So surface area, again, is not too much different. The big thing is this new formula that we sort of need to remember. And then also that you will get to, once you get to the setup, Feel free to use your calculator to integrate. All of our homework is a problem set, so all of our homework is calculated. Oh, yes. So I also want you to think about this. So do you know your derivatives and your integrals of your trig functions? So that is like, do you know all of these derivatives and integrals? So take a second and let's pause the video and let's make sure that we have all of these derivatives and integrals on off the top of our head. Okay, perfect. So now that we have that, let's go through and make sure that we all feel good with these because they are pretty important for us to all know and make sure that we can know and use. So let's start with the easy side. Let's start with our derivatives. So the derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of tangent, secant squared. Derivative of cotangent, negative cosecant squared. Derivative of secant is secant x tangent x. Derivative of cosecant is negative cosecant x, negative cos. Whoops, why did I write a negative again? Negative cosecant x cotangent x. Okay, now the fun ones are integrals. So most of these we should remember. Some of them are probably not our strongest suit. So the integral of sine, negative cosine x plus c. Integral of cosine, sine x plus c. And then we get a little bit more interesting. So in theory, these are ones that you guys knew last year. If you don't, we can either memorize them or reprove them. You can do this one with a u sub. So the integral of tangent is negative natural log of the absolute value of cosine of u, cosine of x, I mean, plus c. Okay? And then the integral of cotangent is similarly the natural log of the absolute value of sine x plus c. Okay? And then the integral of secant, that's another one where we have to do a bit of algebra and trig, is the natural log of the absolute value of secant x plus tangent x plus c. My c doesn't like me. Plus c, my goodness. So pull this over a little bit. There we go. Right. And then the last one that I wanted to write down was the integral of cosecant, which is, of course, again, another natural log, but this time we have that negative. So negative natural log of the absolute value of cosecant x plus cotangent x plus c. Okay, so I just wanted, oops, I'm sorry, I'm dropping things over here. I just wanted to make sure that we had those and are studying those if we don't have them memorized. Awesome. I think that's everything for today. Yep, the homework is problem set 6.4, and that will be in Schoology. So I hope you guys have a great day and reach out if you need anything, and have a great weekend.